Pluto has always been the rebel of our solar system, defying expectations, stirring debates, and hiding secrets that leave scientists scratching their heads. Once considered the ninth planet, its controversial reclassification as a dwarf planet only deepened the intrigue surrounding this distant, icy world. But here's the thing, Pluto isn't just some frozen rock at the edge of our cosmic neighborhood. It's a place of bizarre landscapes, unexplained phenomena, and mysteries that challenge everything we think we know about the outer reaches of space. Imagine a world where icy mountains tower higher than Everest, where nitrogen glaciers creep across the surface, and where the very atmosphere vanishes into thin air only to reappear decades later. This isn't science fiction, this is Pluto. What makes this tiny world so baffling? For starters, its heart-shaped region, Tombaugh Regio, isn't just a quirky feature, it's a geological enigma. Scientists still can't fully explain how it formed or why it's so strikingly different from the rest of Pluto's surface. Then there's the way Pluto interacts with its largest moon, Charon, in a gravitational dance so peculiar it's more like a double planet system than a traditional planet and moon duo. And let's not forget the unexplained dark streaks staining its icy plains, or the fact that Pluto's atmosphere behaves in ways that defy all our models. Every time we think we've got Pluto figured out, it throws another curveball our way. That's why today we're diving deep into the 25 most jaw-dropping, head-scratching mysteries of Pluto, each one a puzzle waiting to be solved. From its chaotic orbit to its bizarre weather patterns, from the possibility of hidden oceans beneath its surface to the strange, glowing haze that envelops it, we'll explore why this little world continues to captivate astronomers and space enthusiasts alike. Whether you're a long-time Pluto defender or just curious about the oddities lurking at the edge of our solar system, this journey promises to challenge what you thought you knew. So buckle up, we're about to venture into the unknown, where every discovery raises more questions than answers, and where Pluto's secrets might just rewrite the story of our cosmic backyard. One of Pluto's most iconic and baffling features is Tombaugh Regio, that massive, heart-shaped region that stole the show when NASA, a New Horizons spacecraft, first revealed it in breathtaking detail. But this isn't just a cosmic coincidence or a cute geological quirk. This heart holds secrets that scientists are still racing to unravel. Stretching over 1,000 miles wide, the left lobe of the heart, known as Sputnik Planitia, is a vast, icy plain filled with nitrogen glaciers that behave almost like a slow-moving liquid. Unlike anything else in the solar system, these glaciers creep across the surface, carving out channels and reshaping the landscape in ways that defy our expectations of how ice should behave on such a cold, distant world. The real mystery, how this heart-shaped feature even formed in the first place. Some researchers believe a colossal impact billions of years ago left behind a giant basin, which then filled with volatile ices like nitrogen, carbon monoxide, and methane. Others argue that subsurface forces, perhaps a hidden ocean or even cryovolcanoes, might be actively reshaping the terrain, pushing nitrogen upward like a slow-motion lava lamp. And then there's the fact that Sputnik Planitia seems perfectly aligned with Pluto's tidal axis, suggesting its gravitational pull might have actually reoriented the entire dwarf planet over time. But the weirdness doesn't stop there. Tombaugh Regio is also responsible for some of Pluto's most dramatic weather patterns. The nitrogen ice evaporates during the dwarf planet's long, slow summers, creating a thin, hazy atmosphere that refreezes onto the surface during its extended winters. This cycle could explain the strange, churning cells of ice visible in Sputnik Planitia, almost like a boiling pot of liquid nitrogen, except here, the processes take centuries. With no other known place in the solar system exhibiting such extreme behavior, Pluto's heart remains one of the most puzzling geological puzzles we've ever encountered. Every new theory only seems to deepen the mystery, proving that even at the edge of the solar system, Pluto's got a lot more going on beneath the surface than we ever imagined. Sputnik Planitia isn't just a strange patch of ice. It's a window into Pluto's hidden mechanics, and its peculiar alignment tells a story unlike anything else in the solar system. This sprawling basin, roughly the size of Texas, sits almost perfectly opposite Pluto's largest moon, Charon, as if locked in place by some unseen cosmic tug of war. That's no accident. Scientists believe the sheer weight of the nitrogen ice filling Sputnik Planitia may have shifted Pluto's entire orientation over billions of years, literally tipping the dwarf planet to keep this massive depression fixed in line with its tidal axis. It's as if Pluto rebalanced itself to keep this one feature centered, a phenomenon that challenges our understanding of how small planetary bodies evolve. But what really fuels the intrigue is what might lie beneath the ice. The basin's eerie smoothness and lack of impact craters suggest something dynamic is at work, possibly a subsurface ocean churning below the surface. If true, this hidden body of water, kept liquid by radioactive heat or tidal forces from Charon, could be helping to replenish the ice above, smoothing out the terrain like a slow-motion resurfacing machine. Even more tantalizing, the way cracks and ridges around Sputnik Planitia resemble the icy crusts of moons like Europa and Enceladus, where subsurface oceans are known to exist. If Pluto has its own buried sea, it would redefine our ideas about where liquid water, and perhaps even the ingredients for life, can exist in the solar system. Yet Sputnik Planitia's quirks don't stop there. The ice here isn't just frozen water. It's a volatile mix of nitrogen, carbon monoxide, and methane, behaving more like putty than solid ground. These ices flow in sluggish rivers, creating bizarre polygonal shapes that look like the cells of a giant cosmic beehive. Scientists think convection currents, driven by slight heat differences, might be pushing this material upward in some spots while pulling it down in others, a process so alien that Earth has no direct comparison. Add in the fact that Pluto's tenuous atmosphere freezes and thaws over its centuries-long seasons, dusting the basin with fresh ice like some slow-motion snow globe, and you've got a landscape that feels more like a scientific riddle than a simple geological feature. Every clue we uncover about Sputnik Planitia only leads to more questions, proving that even in the solar system's frozen outskirts, the most unassuming places can hold the wildest secrets. Pluto's atmosphere is as unpredictable as the dwarf planet itself, vanishing, reappearing, and transforming in ways that leave scientists utterly baffled. Unlike Earth's stable, predictable air, Pluto's wispy shroud of nitrogen, methane, and carbon monoxide behaves more like a cosmic magician's trick, expanding and contracting with no apparent rhyme or reason. When NASA New Horizons spacecraft zipped past in 2015, it revealed an atmosphere nearly 1,000 miles high, far thicker than anyone had anticipated. Yet just a few years later, observations from Earth showed it had dramatically collapsed like a deflating balloon. This isn't just a minor fluctuation, it's a full-scale rebellion against our models of how planetary atmospheres should work. What's driving this wild volatility? One key factor is Pluto's extreme orbit, which sends it looping around the Sun in a lopsided 248-year journey. At its closest approach, sunlight warms the icy surface just enough to vaporize frozen nitrogen and methane, puffing up the atmosphere. But as Pluto retreats to the frigid outer reaches of its orbit, that same atmosphere should theoretically freeze solid and crash back to the ground. Except it doesn't, at least not completely. Even when Pluto is farthest from the Sun, traces of its atmosphere cling stubbornly to existence, defying the laws of physics as we understand them. Some researchers suspect underground reservoirs of volatile ices might be slowly leaking gases, like a planetary-scale slow cooker keeping the atmosphere on life support. Others propose that complex chemical reactions in Pluto's haze layers could be generating just enough heat to stave off total collapse. Then there's the role of Pluto's bizarre seasons. With an axial tilt of 120 degrees, imagine a spinning top nearly toppled over. The dwarf planet experiences wild swings in sunlight distribution over centuries-long seasons. During certain phases, entire hemispheres plunge into decades of permanent twilight, while others bake in continuous, if feeble, sunlight. This uneven heating likely triggers bizarre atmospheric tides, where gases migrate from one pole to the other, creating pressure imbalances that could explain some of the erratic behavior. But here's the real kicker. Even with all these factors, computer simulations still can't fully replicate Pluto's atmospheric antics. Every tweak to the models only highlights how much we're missing about the delicate interplay between surface ice, solar radiation, and subsurface dynamics on this tiny world. Perhaps the most tantalizing clue lies in the blue haze layer's new horizons spotted high above Pluto's surface. These shimmering veils, likely formed when sunlight breaks apart methane molecules, shouldn't exist at such altitudes unless unknown forces are lofting particles upward or generating fresh gases in the atmosphere itself. Some scientists speculate that microscopic organic compounds created by reactions in the haze might be acting like tiny heat absorbers, subtly altering atmospheric pressure in ways we haven't yet grasped. It's a reminder that Pluto, for all its distance, isn't just a frozen relic of the solar system's past. It's a dynamic, ever-changing world with an atmosphere that refuses to follow the rules, and that's what makes it one of the most compelling mysteries at the edge of our cosmic neighborhood. Pluto's shimmering haze layers are one of the most visually striking and chemically confusing features of this distant world. When New Horizons captured images of the dwarf planet backlit by the sun, it revealed towering blue veils stretching hundreds of miles above the surface, far higher than any atmospheric haze should logically be. These aren't just wispy clouds, they're structured into distinct layers like the rings of a celestial onion, each one holding clues to Pluto's strange atmospheric chemistry. What makes this phenomenon so puzzling isn't just the haze itself, but the fact that it exists at all. At such extreme altitudes, the atmosphere should be too thin to support visible particles, yet there they are, glowing like an ethereal halo around the tiny world. The secret might lie in a sinister-sounding class of compounds called tholins. These complex molecules form when ultraviolet radiation from the sun slams into methane and nitrogen in Pluto's upper atmosphere, breaking them apart and allowing the fragments to recombine into larger, more complicated structures. Tholins are responsible for the haze's reddish-brown tint, when viewed up close, the same organic gunk that stains areas of Pluto's surface with dark, rusty patches. But here's the twist: these particles shouldn't be able to linger so high up. On Earth, gravity would quickly drag them down, yet on Pluto, something is continuously lofting them skyward. Some scientists suspect that subtle atmospheric waves, generated by Pluto's rugged terrain below, could be acting like an invisible elevator, pushing tholins upward against the pull of gravity. Others theorize that the particles themselves might be incredibly lightweight, almost like cosmic soot, allowing them to stay suspended far longer than expected. Then there's the temperature paradox. Pluto's upper atmosphere is much warmer than predicted, not exactly balmy, but definitely hotter than the frigid surface. This extra heat might come from the haze layers themselves. As tholins absorb sunlight, they could release energy back into the atmosphere, creating a feedback loop that sustains the very environment that formed them. It's a delicate, self-perpetuating cycle that blurs the line between cause and effect. Even more intriguing, these haze layers might hold the key to Pluto's bizarre, disappearing and reappearing atmosphere. The same organic compounds could be acting like a slow-release battery, storing solar energy and gradually redistributing it to stabilize the dwarf planet's tenuous air over decades. But the biggest mystery remains the layers themselves. Why do they form in such distinct, separated bands instead of blending into a uniform haze? One possibility involves gravity waves, not to be confused with gravitational waves from black holes, but the atmospheric kind, created when air flows over mountains or other obstacles. These waves could create alternating zones of rising and sinking air, concentrating tholins into discrete sheets like ripples frozen in time. Another theory points to seasonal shifts, with sunlight triggering chemical reactions that ebb and flow over Pluto's centuries-long year, leaving behind a layered record of atmospheric changes. Whatever the explanation, these hazes are more than just a pretty spectacle. They're a dynamic, evolving puzzle, one that challenges our understanding of how even the smallest, coldest worlds can host atmospheres far more complex than we ever imagined. If Pluto has one thing in abundance, it's surprises, and Right Mons might be the most intriguing of them all. Towering over 2.5 miles high and stretching nearly 100 miles wide, this bizarre, blister-like mountain doesn't look like any volcano we've seen on Earth or elsewhere in the solar system. Dubbed a potential cryovolcano, Right Mons could be evidence that Pluto isn't just a frozen wasteland but a geologically active world where eruptions don't spew lava. They belch slushy mixtures of water, ammonia, or methane. But here's the twist. Scientists still can't agree whether this giant mound is truly a volcano or just an oddball formation sculpted by time and temperature swings. The case for cryovolcanism hinges on Right Mons' peculiar structure. Unlike the steep, conical volcanoes of Earth or Mars, this feature has a shallow, wrinkled summit with a deep central depression, almost like a deflated soufflé. Surrounding it are sprawling, lumpy terrains that resemble frozen flows, as if some thick, icy goo oozed across the surface before solidifying. If this was indeed a cryovolcano, the magma here wouldn't be molten rock but a strange cocktail of substances like supercooled water mixed with antifreeze like ammonia or even pockets of slushy nitrogen. These exotic blends could remain liquid or at least malleable at temperatures hundreds of degrees below zero, seeping upward through cracks in Pluto's crust before freezing into the chaotic landscapes we see today. But skeptics point to alternative explanations. Without clear vent structures or fresh deposits, Right Mons might just be an ancient relic, sculpted by the slow sublimation of volatile ices under Pluto's weak sunlight. Imagine a block of dry ice left to wither away its surface, pitting and cracking unpredictably over millennia. Some researchers argue that what we're seeing isn't volcanic activity but the ghost of past climate cycles, where Pluto's ever-shifting atmosphere etched peculiar scars into the terrain. The smoking gun, or rather, the freezing gun, might lie in Pluto's chemistry. If future missions detect certain organic compounds or crystalline structures around Right Mons, it could confirm that material once erupted from below. Even more tantalizing is the possibility that these cryovolcanoes, if real, could be windows into a subsurface ocean. On moons like Europa and Enceladus, similar processes create plumes that jet water into space. If Pluto's interior hides even a trace of liquid erupting through these icy vents, it would force us to rethink how tiny, distant worlds retain heat and stay geologically alive. For now, Right Mons remains a captivating mystery, a mountain that defies easy labels and invites us to question what we know about geologic activity in the solar system's farthest reaches. Whether it's a dormant cryovolcano, an eroded oddity, or something entirely unexpected, one thing's certain: Pluto isn't done keeping us guessing. Among Pluto's many oddities, the dark streaks staining its icy plains stand out as one of the most visually striking and least understood features. These elongated smudges, some stretching dozens of miles across the surface, seem almost like giant brushstrokes painted onto the dwarf planet's frozen canvas. But what's creating them? Unlike the dark patches found on Mars or the Moon, which are often explained by ancient lava flows or impact debris, Pluto's streaks defy easy categorization. Their sheer length and alignment suggest some kind of directional force at work, whether it's wind, ice sublimation, or even seasonal outgassing. Yet on a world with an atmosphere barely 100,000th as thick as Earth's, the idea of wind carving such dramatic features seems almost impossible. One leading theory points to sublimation, the process where ice transforms directly into gas, skipping the liquid phase entirely. As Pluto's nitrogen and methane ices warm under the faint sunlight, they might be vaporizing unevenly, leaving behind darker, more resistant materials like tholins. These organic compounds, formed when sunlight breaks down methane in Pluto's atmosphere, could accumulate on the surface like cosmic soot, creating the streaked patterns we see. But here's the catch: these streaks aren't randomly scattered. They cluster in specific regions, often near the edges of ice plains or along ridge lines, hinting at a deeper geological or even meteorological process. Some scientists propose that weak winds, yes, even in Pluto's whisper-thin atmosphere, might be redistributing these dark particles in linear patterns, like sand dunes shaped by a gentle breeze. Others suggest that seasonal changes in ice composition could be causing the surface to crack and vent gases, carrying dark material along predictable pathways. What makes these streaks even more puzzling is how they compare to similar features elsewhere in the solar system. On Mars, dark slope streaks are often linked to dust avalanches triggered by dry ice sublimation. On Neptune's moon Triton, geysers of nitrogen gas blast dark material across the surface, creating fan-like deposits. Yet Pluto's streaks don't perfectly match either model. They're too uniform for geysers, too organized for simple avalanches. Could a combination of processes be at work, or is Pluto hiding an entirely new mechanism we haven't identified yet? The answer might lie in the way Pluto's volatile ices interact with its environment. Unlike water ice, nitrogen and methane can shift between solid and gas states under surprisingly low pressure and temperature conditions. This means even subtle changes in sunlight or subsurface heat could trigger dramatic surface transformations over time. Imagine a glacier that doesn't just melt, it vanishes into thin air, leaving behind streaks of concentrated residue. Add in the possibility of seasonal winds, powered by temperature differences between ice-covered and bare terrain, and you've got a recipe for some truly alien geology. For now, the dark streaks remain a testament to Pluto's complexity, a reminder that even in the frigid reaches of the Kuiper Belt, dynamic forces are at work, sculpting landscapes in ways we're only beginning to decode. Whether sculpted by wind, sublimation, or something even stranger, these features challenge our assumptions about what's possible on a world so small and so far from the Sun. Every new image of Pluto seems to add another layer to the mystery, proving that this tiny dwarf planet has a lot more going on beneath the surface, literally and figuratively, than we ever expected. Pluto's chaotic terrain looks like something out of a surrealist painting: towering blades of ice, fractured plateaus, and crumpled landscapes that defy logic. Take Tartarus Dorsa, a region nicknamed the Bladed Terrain for its jagged, knife-like ridges stretching hundreds of feet into the sky. These aren't ordinary mountains, they're more like frozen fangs, clustered so densely they create a maze of shadows and light. What could possibly sculpt such a bizarre environment? The answer might lie in Pluto's volatile cocktail of ices and its extreme seasonal swings, where the very ground seems to breathe over millennia. Scientists suspect these jagged formations are made primarily of methane ice, hardened into razor-sharp edges by processes unlike anything on Earth. One leading theory suggests that over millions of years, Pluto's thin atmosphere allows methane to sublimate, transitioning directly from solid to gas, leaving behind these skeletal ridges as weaker materials vanish. Imagine a block of dry ice slowly eroding in the sun, but on a planetary scale, with cycles of freezing and thawing sculpting the landscape into something otherworldly. Another possibility points to seasonal methane snowfall, When Pluto's temperature dips, methane in the atmosphere might condense and blanket the surface, only to be carved into spines by sublimation as temperatures rise. It's a slow-motion dance between deposition and destruction, creating terrain that looks more like a frozen alien city than a natural geological feature. But methane alone might not tell the whole story. Some researchers argue that tectonic forces could be at work, with Pluto's crust cracking and shifting due to stresses from its odd gravitational relationship with Charon. The bladed terrain often borders smoother plains, suggesting underground melting or even cryovolcanic activity might be softening and distorting the terrain at the edges. There's also the wild card of nitrogen glaciers. Could their slow, creeping flow be shearing the methane ice into these dramatic formations? The closer we look, the more questions arise. What makes Tartarus dorsa even more perplexing is its uneven distribution. These spires aren't scattered randomly, they cluster in specific zones, often near the boundaries of Pluto's major geological provinces. This hints at a deeper global process, perhaps heat seeping from below or ancient impacts disrupting the ice in ways we don't yet understand. Even the orientation of the blades seems deliberate, aligned in ways that suggest wind patterns or solar exposure played a role in their formation. Yet Pluto's atmosphere is far too thin for typical wind erosion, and sunlight at that distance is a faint whisper. The bladed terrain isn't just a geological oddity, it's a window into Pluto's resilience. This tiny world, once written off as a static ice ball, is clearly alive with activity, just on timescales we're only beginning to grasp, whether shaped by sublimation, tectonics, or some yet undiscovered force. Tartarus dorsa stands as a testament to the fact that even in the solar system's furthest reaches, nature finds ways to surprise us. And if there's one thing Pluto has taught us, it's that the most alien landscapes often hold the keys to understanding how planetary processes work in the most unexpected places. Pluto's rusty, blood-red hue isn't just for show. It's the fingerprint of a chemical drama playing out across its frozen surface. Unlike the vivid blues of Neptune or the dusty orange of Mars, Pluto's coloration comes from a sinister-sounding process involving cosmic radiation, frozen gases, and a class of organic compounds called tholins. These complex molecules form when ultraviolet light and charged particles from the Sun bombard methane and nitrogen in Pluto's thin atmosphere, shattering them into fragments that recombine into larger, reddish-brown compounds. Over billions of years, these tholins drift down like sticky, organic snow, staining the dwarf planet's icy plains with their distinctive tint. But here's the mystery. Why are some regions of Pluto drenched in this ruddy veneer while others remain pale or even starkly white? The answer lies in Pluto's uneven landscape and the volatile nature of its ices. In places like Tombaugh Regio's western lobe, the bright, heart-shaped Sputnik Planitia, fresh nitrogen glaciers constantly renew the surface, burying older, tholin-stained layers under pristine ice. Meanwhile, darker, redder regions like Cthulhu Macula, a sprawling equatorial belt, show signs of ancient terrain where tholins have accumulated undisturbed for eons. The contrast is stark. Imagine a freshly zambonied ice rink next to a weather-beaten barn. But it's not just age at play. Temperature variations cause nitrogen and methane ices to sublimate at different rates, leaving behind concentrated deposits of tholins in some areas while whisking them away in others. High-altitude regions exposed to more UV radiation often appear redder because the atmospheric reactions producing tholins are supercharged there. Then there's Pluto's chaotic climate. During its centuries-long seasons, sunlight triggers chemical reactions that can intensify or fade the redness. When the dwarf planet's atmosphere briefly swells during its closest approach to the Sun, the increased methane concentration fuels more tholin production like a seasonal paint factory operating in overdrive. But as Pluto retreats into the deep freeze, this process slows, allowing other forces like micrometeorite impacts or subsurface geological activity to redistribute or even erase the colored patches. What makes Pluto's palette even more fascinating is how it compares to other bodies in the outer solar system. Saturn's moon Titan and Neptune's Triton also sport Tholen-based hues, but Pluto's coloration is uniquely patchy, suggesting a dynamic interplay between atmosphere, surface chemistry, and geology that we haven't seen elsewhere. Some scientists speculate that cryovolcanoes or hidden liquid reservoirs might be locally replenishing the ice, resetting the clock on Tholen accumulation in certain spots. Others point to wind patterns in Pluto's wispy atmosphere. Yes, even a trace breeze could nudge lightweight Tholen particles into drifts, creating streaks and blotches of concentrated color. Ultimately, Pluto's ruddy complexion is more than skin deep. It's a living record of the dwarf planet's atmosphere, climate history, and even its potential internal activity. Every shade of red tells a story of sunlight breaking apart molecules, of ices vanishing into the void, and of a tiny world whose surface is anything but frozen in time. Pluto's moons don't follow the rules. They dance to a rhythm all their own, spinning and swaying in orbits so chaotic they've left astronomers downright perplexed. While Charon, Pluto's largest moon, dominates the scene with its gravitational grip, the dwarf planet's four smaller companions Nix, Hydra, Kerberos, and Styx are anything but orderly. These tiny worlds tumble through space like drunks staggering home, wobbling unpredictably as they orbit the Pluto-Charon duo. Their paths are so erratic that even the most advanced simulations struggle to predict their movements. One moment, Nix might be spinning backward, the next, Hydra could be flipping like a coin mid-orbit. It's a celestial free-for-all, and the root of this chaos lies in the gravitational tug-of-war between Pluto and its overgrown moon, Charon. The real shocker, Charon isn't just a moon, it's a co-conspirator in this orbital anarchy. At half the size of Pluto, Charon doesn't orbit the dwarf planet so much as the two swing around a shared point in space, like a pair of figure skaters locked in a spin. This creates a gravitational environment unlike anything else in our solar system, where the usual orderly moon-planet relationships break down. The smaller moons caught in this cosmic crossfire are jostled by competing forces, their orbits stretched and twisted over time. Some scientists compare them to pinballs ricocheting between Pluto and Charon, their paths reshaped by every subtle gravitational nudge, but gravity alone can't explain the full spectacle. Nix and Hydra, for instance, rotate so wildly that their north and south poles might swap places over time, a phenomenon astronomers call chaotic rotation. Imagine a top spinning so unevenly it occasionally flips upside down, only to right itself hours or days later. Kerberos and Styx, meanwhile, move in delicate, synchronized orbits as if choreographed by some unseen celestial hand. This bizarre harmony, known as orbital resonance, suggests they might be the survivors of ancient collisions, their current path shaped by violent encounters long ago. And that's where the real mystery kicks in. Did these moons form alongside Pluto and Charon, or are they the shattered remnants of a catastrophic impact? Some researchers argue their odd shapes, lumpy, elongated, and far from spherical, hint at a violent past where smaller bodies smashed together and coalesced into the irregular worlds we see today. Others speculate that gravitational interactions might have pulled them apart and reassembled them over eons, like cosmic Lego sets perpetually rebuilding themselves. What's undeniable is that Pluto's moon system defies expectations at every turn. Even the New Horizons spacecraft, which flew past in 2015, couldn't fully unravel their secrets, revealing surfaces pockmarked by craters, yet suspiciously bright in some areas, as if fresh ice had recently risen to the surface. Are these moons geologically active? Could tidal forces from Pluto and Charon be heating their interiors, creating subsurface slush that occasionally bursts forth? The more we learn, the clearer it becomes. Pluto's moons aren't just passive spectators in the outer solar system's drama. They're dynamic, unpredictable players, rewriting the rules of orbital mechanics with every erratic spin and wobble. And somewhere in their chaotic dance, they might just hold the key to understanding how small, icy worlds survive and thrive in the most turbulent corners of space. Charon's North Pole looks like it's been dipped in ink, a sprawling, rust-colored blotch nicknamed Mordor Macula, as if the moon borrowed its name straight from Tolkien's shadowy realm. This eerie dark spot, spanning over 200 miles, isn't just a quirk of coloration. It's a window into the bizarre chemistry playing out between Pluto and its largest moon. When New Horizons captured the first close-up images of Charon in 2015, scientists expected a dull, cratered ice ball. Instead, they found a world with a dramatic two-tone complexion, pale plains slashed by a polar stain so vivid it seemed painted on. So what's behind this ominous feature? One leading theory points to Pluto itself as the culprit. Charon and Pluto are locked in such a tight gravitational embrace that gases escaping Pluto's atmosphere, particularly methane, might be drifting across the void and settling on Charon's frigid poles. Over time, this captured methane could be transformed by solar radiation into heavier, darker compounds. Imagine sunlight breaking apart methane molecules like a cosmic blender, leaving behind a residue of complex hydrocarbons and tholins, the same reddish-brown gunk staining parts of Pluto. But here's the twist: this process shouldn't be uniform. Why does only one pole look like it's been singed? The answer might lie in Charon's extreme seasons. Unlike Pluto, which wobbles dramatically on its axis, Charon's tilt is far more subdued, yet its poles still endure decades of unbroken sunlight or darkness during the dwarf planet system's long orbit around the Sun. During these extended winters, temperatures at the poles plunge so low that any methane lingering there freezes into a thin frost. When sunlight finally returns, it doesn't just warm the ice, it weaponizes it. Ultraviolet radiation bombards the frozen methane, stripping away hydrogen atoms and leaving behind carbon-rich sludge. Over millennia, this cycle could have built up Mordor Macula layer by layer, like a slow-motion chemical tattoo. But there's another, even wilder possibility. Charon might be making its own darkness. Some researchers suggest that trace amounts of methane trapped beneath the moon's surface could be seeping out through cracks or ancient cryovolcanic vents, pooling at the poles where radiation processes them into that distinctive red. If true, it would mean Charon isn't just a passive recipient of Pluto's atmospheric leaks, it's an active participant in its own staining. The real puzzle, though, is the spot's sharp boundaries. Unlike Pluto's blotchy tholin stains, Mordor Macula has an almost geometric edge, as if someone drew a line across Charon's face and said, "Paint everything north of this." One explanation involves Charon's frigid polar cold traps regions so chilly they effectively corral volatile compounds, preventing them from spreading equatorward. Another theory points to magnetic fields, though Charon isn't known to have a strong one. Could electrostatic forces be at play, organizing particles like iron filings on a sheet of paper? Whatever the mechanism, Mordor Macula isn't just a curiosity. It's evidence of a dynamic relationship between Pluto and Charon that's still unfolding. The same processes tinting this moon's pole might be subtly altering Pluto's atmosphere, creating feedback loops we're only beginning to trace. And if tiny, icy worlds like Charon can host chemistry this complex, what other surprises are hiding in the darkness at the edge of our solar system? One thing's certain, that Inkai stain is more than just a splash of color. It's a signature, a silent testament to the forces shaping worlds even in the deepest freeze. Pluto's surface is a patchwork of contradictions, but nothing defies expectations quite like its eerie lack of craters. In some regions, like the vast, heart-shaped Sputnik Planitia, the ground is suspiciously smooth, almost as if someone took a cosmic spatula and scraped away the scars of billions of years of impact. This isn't just a minor oddity, it's a glaring clue that Pluto, despite its distance from the Sun, might still be geologically alive. Craters are the solar system's history books, recording every collision over eons. So when a world as ancient as Pluto shows patches nearly devoid of them, it's like finding a blank page in the middle of a novel. Something is erasing the evidence. The leading theory, active resurfacing. On most icy bodies in the outer solar system, craters stick around indefinitely, frozen in time like fingerprints on a cold doorknob. But Pluto's nitrogen, methane, and carbon monoxide ices behave differently. These volatile compounds can flow like glaciers, albeit at a pace measured in centuries rather than years. Sputnik Planet's churning, convective cells, those strange polygonal patterns spotted by New Horizons, hint at a surface slowly renewing itself, with warmer ice rising from below while older material sinks and vanishes. Imagine a pot of thick soup simmering on low heat, its surface constantly rearranging itself to hide any bubbles that burst. That might be what's happening on Pluto, with its icy crust recycling so gradually that impacts fade before they can accumulate. But glaciers alone might not explain the full picture. Some scientists point to Pluto's vanishing atmosphere as a potential sculptor. When the dwarf planet swings closer to the Sun, its thin atmosphere briefly thickens, allowing nitrogen and methane to vaporize and redistribute across the surface. This seasonal cycle could be sandblasting away smaller craters, filling them in with fresh frost like nature's own spackle. Meanwhile, larger impacts might trigger localized melting, their heat briefly liquefying subsurface ices that then refreeze into smooth plains. There's even a chance cryovolcanoes like Right Mons are contributing, spewing slushy mixtures that blanket older terrain in glossy new layers. Then there's the wild card, sublimation erosion. Unlike Earth, where craters erode from wind and rain, Pluto's version of weathering happens when sunlight transforms surface ices directly into gas. Over millennia, this process could be sanding down crater rims or collapsing their walls, leaving behind shallow depressions that eventually vanish entirely. It's a slow-motion disappearing act, one that might explain why some of Pluto's craters look oddly deflated, like balloons losing air. The implications are staggering. If Pluto is still resurfacing itself today, it means this tiny world harbors internal heat sources, whether from radioactive decay, tidal interactions with Charon, or even a subterranean ocean. That heat wouldn't just smooth the surface, it could maintain liquid water beneath the ice, raising the tantalizing possibility of habitable niches in the solar system's frozen fringe. Even the most conservative estimates suggest some of Pluto's terrain is no more than 10 million years old, a blink in geological time and proof that the dwarf planet hasn't settled into quiet retirement. Yet for all the evidence, mysteries remain. Why do some regions, like the dark highlands of Cthulhu Macula, remain heavily cratered while others stay pristine? Does Pluto's resurfacing happen in global waves, or is it a patchwork of local phenomena? And if the dwarf planet is still geologically active, what does that mean for other Kuiper Belt objects? Every unanswered question is a reminder that Pluto, for all its small size, operates on a cosmic scale, where the slow creep of ice and the whisper of escaping gases can rewrite an entire world's surface, leaving us to piece together the story from the gaps it leaves behind. Pluto's Tartarus Dorsa isn't just another rugged landscape, it's a nightmare of frozen spikes, a jagged maze of methane ice blades that rise like the serrated teeth of some cosmic beast. Dubbed the snakeskin terrain for its reptilian texture, this equatorial belt of towering spines defies every expectation of what a frozen world should look like. Some of these blades stretch taller than skyscrapers, their edges sharpened by eons of sublimation where sunlight turns ice directly into vapor, leaving behind skeletal ridges of pure methane. But why here? Why do these eerie formations cluster along Pluto's equator, while other regions remain smooth or pockmarked with craters? The answer lies in a delicate interplay of chemistry, climate, and celestial mechanics unlike anything else in the solar system. Methane is the key player in this frozen drama. Unlike water ice, which stays rigid even in Pluto's bitter cold, methane ice is volatile, responsive to the faintest whispers of solar warmth. At the equator, where sunlight strikes most directly, temperatures fluctuate just enough to trigger a slow-motion cycle of evaporation and recondensation. Over millions of years, this process carves the ice into those iconic blades, like a sculptor working in ultra-slow motion. But there's a twist: these spines aren't random. They align in near-perfect rows, suggesting something more organized than simple weathering. Some scientists believe Pluto's weak winds, though barely perceptible, could be guiding the sublimation process, etching the ice into uniform patterns as gases escape in preferred directions. Others point to seasonal methane snowfall. Imagine a brief equatorial frost that later sculpts itself into spines as the ice retreats unevenly under the sun's gaze. The snakeskin terrain's equatorial exclusivity adds another layer of intrigue. Pluto's poles and mid-latitudes host vastly different landscapes: glaciers of nitrogen, sprawling plains, even potential cryovolcanoes, but nothing like Tartarus Dorsa's razor-edged chaos. This stark divide hints at a climate boundary where temperature and sunlight thresholds create a Goldilocks zone for blade formation. Too close to the poles, and the methane stays frozen in place. Too far, and it sublimates away too quickly to leave behind those dramatic spines. The equator, it seems, is just right. A narrow band where conditions conspire to freeze, thaw, and refreeze methane in a way that builds these structures millimeter by millimeter over millennia. Yet even this explanation might not capture the full picture. New Horizons spotted similar, albeit smaller, blade-like features on other methane-rich worlds like Neptune's moon Triton. But Pluto's versions are larger, more organized, and far more widespread, suggesting something unique about its environment. Could tidal forces from Charon be flexing Pluto's crust, creating microfractures that guide blade growth? Or does the dwarf planet's wobbly axial tilt, a staggering 120 degrees, drive such extreme seasonal shifts that equatorial ice undergoes phases of explosive sublimation? The more we study Tartarus Dorsa, the clearer it becomes. This isn't just a geological oddity. It's a laboratory for understanding how volatile ices behave in the solar system's most extreme environments. A place where the rules of chemistry and physics write themselves in frozen, razor-sharp ink. And perhaps the most haunting question of all, if methane blades can grow here, what other alien landscapes might be hiding in the Kuiper belt, waiting to rewrite our textbooks? Pluto's snakeskin terrain is a reminder that even in the darkest, coldest reaches of space, nature finds ways to surprise us one spine at a time. Pluto's glaciers shouldn't exist, at least not the way we know them. On Earth, glaciers creep downhill under the weight of compacted snow, sculpted by gravity and liquid water lubricating their base. But on Pluto, the glaciers are made of nitrogen ice, crawling across the surface at temperatures barely 40 degrees above absolute zero, where the very concept of downhill takes on an alien meaning. These aren't just frozen slabs, they're dynamic rivers of ice, reshaping Pluto's landscape in ways that mirror earthly geology, yet operate on rules written by another universe entirely. Take Sputnik Planitia, the western half of Pluto's heart-shaped Tombaugh Regio. This sprawling basin is packed with nitrogen glaciers so vast they could swallow entire countries, flowing in slow-motion currents that defy intuition. Unlike Earth's water ice, nitrogen ice is soft and malleable even in Pluto's deep freeze, behaving more like thick syrup than solid rock under the dwarf planet's faint gravity. Satellite images reveal intricate patterns, convective cells the size of cities, where warmer ice wells up from below while older material sinks, creating a churning, hexagon-tiled surface that looks like the world's largest cosmic honeycomb. But what's powering this movement? On Earth, glacial flow relies on geothermal heat and the sun's energy. Pluto, nearly 40 times farther from the sun than we are, shouldn't have enough warmth to budge a snowflake, let alone an entire ice sheet. The answer lies in Pluto's hidden energy reserves. While sunlight at that distance is feeble, the dwarf planet's internal heat might be anything but. Radioactive decay in Pluto's rocky core could be generating just enough warmth to soften the nitrogen ice from below, allowing it to ooze across the surface like cold molasses. There's also the wild card of phase changes, the way nitrogen transitions between solid, liquid, and gas states under minuscule temperature shifts. Even a fraction of a degree difference might be enough to trigger sublimation or refreezing, creating pressure imbalances that nudge the glaciers forward. Add Pluto's bizarre axial tilt, which creates extreme seasonal variations over centuries-long cycles, and you've got a recipe for glacial movement fueled by celestial chaos. Then there's the role of other exotic ices. Mixed into Pluto's nitrogen glaciers are traces of carbon monoxide and methane, which alter the flow dynamics in ways scientists are still untangling. These contaminants might act like antifreeze, lowering the melting point of nitrogen just enough to keep it mobile, or they could create brittle layers that fracture under stress, causing the ice to break into floating rafts, some of which appear to have drifted across Sputnik Planitia, leaving trails like ships cutting through a frozen sea. The most mind-bending part, these glaciers might be erasing Pluto's history. As they inch forward, they bury craters, smooth over cracks, and recycle the surface like a cosmic etch-a-sketch. That's why regions like Sputnik Planitia look eerily young compared to Pluto's craggier highlands. The nitrogen ice isn't just flowing, it's rewriting the dwarf planet's geological record, one sluggish millimeter at a time. What's staggering is how these processes mirror Earth's glacial activity despite the unimaginable differences in environment. Both worlds feature ice that deforms, flows, and carves valleys, just with materials and timescales alien to each other. It's a reminder that geology isn't bound by a single set of rules. Whether it's water on Earth or nitrogen on Pluto, the universe finds ways to sculpt landscapes that feel eerily familiar yet utterly alien. And somewhere in that paradox lies the key to understanding not just Pluto, but how icy worlds across the cosmos evolve in silence, in cold, and in ways we're only beginning to decipher. Stretching across Pluto's equator like a shadowy leviathan, Cthulhu Macula is one of the dwarf planet's most striking features, a sprawling, dark region nicknamed the Whale for its unmistakable silhouette. This elongated blotch, over 1,800 miles long, isn't just a trick of the light. Its deep reddish-brown hue stands in stark contrast to the bright, icy plains of nearby Tombaugh Regio, as if someone spilled ink across half the planet. But what gives this area its Inkai stain? The answer lies in a cosmic chemistry experiment playing out over billions of years, where sunlight transforms simple molecules into a complex cocktail of organic compounds. Cthulhu Macula's darkness comes from tholins, the same mysterious, carbon-rich gunk tinting other parts of Pluto. But here, the tholins aren't just a thin veneer, they're piled deep, suggesting this region has been a dumping ground for atmospheric fallout far longer than anywhere else on the dwarf planet. Unlike the youthful, resurfaced terrain of Sputnik Planitia, see Thul, whose surface is ancient, its cratered landscape betraying little geological activity to refresh or erase its somber tones. It's as if this part of Pluto has been collecting cosmic soot since the dawn of the solar system, preserved in a frozen time capsule. How did this vast stain form? One theory points to Pluto's chaotic seasons. As the dwarf planet wobbles on its extreme axial tilt, sunlight strikes different latitudes at varying intensities over millennia. Cthulhu Macula, straddling the equator, may have spent eons bathed in just enough sunlight to trigger tholin production, but not enough to vaporize or redistribute the resulting gunk. Like a slow cooker left on low, the region could have simmered in UV radiation, its ices gradually baking into ever darker compounds. Another possibility involves Pluto's atmosphere. When the dwarf planet swings closer to the Sun, its nitrogen and methane gases briefly puff up, only to freeze out again as it retreats. Over countless cycles, these gases might preferentially condense onto whose colder highlands, creating a feedback loop where darker surfaces absorb more heat, driving further tholin formation. Yet composition alone doesn't explain the whale's odd shape. Why does this stain follow such a distinct, cohesive outline rather than scattering like paint splatters? The answer might lie beneath the surface. Radar studies suggest Cthulhu macula sits atop older, water ice bedrock material far less volatile than the nitrogen and methane ices covering Sputnik Planitia. This bedrock could act like a canvas, holding tholins in place while softer ices around it sublimate away, carving the whale's sharp edges. Some researchers even speculate that tectonic forces lifted this region long ago, exposing ancient tholin-rich layers to relentless radiation. What's most intriguing, though, is what Cthulhu macula might be hiding. Tholins aren't just stains, they're the building blocks of more complex organic molecules, the kind that could seed prebiotic chemistry. If Pluto's dark whale contains pockets of preserved primordial material, it could offer clues about how life's ingredients spread through the solar system. Every crack and crater in this ancient terrain might be a page in a story we're only beginning to read, one written not in ink but in the slow, silent alchemy of ice and light. Pluto isn't just a distant, frozen rock. It's a cosmic chameleon, shifting in brightness like a flickering light bulb at the edge of the solar system. Over decades of observations, astronomers have watched its surface reflectivity fluctuate unpredictably, sometimes growing noticeably darker, other times gleaming brighter for reasons that defy simple explanation. This isn't just a trick of the light, it's evidence of a world in constant, slow-motion transformation, where entire landscapes rewrite themselves in response to the faintest whispers of solar warmth. The key lies in Pluto's volatile ices, substances like nitrogen, methane, and carbon monoxide that don't just freeze and melt like water ice, but sublimate directly from solid to gas under the slightest temperature nudge. Imagine stepping onto Pluto's surface during its centuries-long summer, where sunlight, though weak, warms the ground just enough to vaporize patches of nitrogen ice. These escaping gases carry tiny particles of darker tholins aloft, dusting the surface like soot from a smokestack and dimming its overall reflectivity. Then, as Pluto retreats into winter, those same gases freeze back onto the ground, frosting the terrain with fresh, bright ice that boosts its shine. It's a planetary scale cycle of evaporation and condensation, playing out over timescales no human could witness in a lifetime. But here's the catch: these changes aren't uniform. Some regions, like the heart-shaped Tombaugh Regio, refresh their surfaces so rapidly they stay persistently bright, while darker areas like Cthulhu macula cling stubbornly to their ruddy hues, resisting the cycle. What makes Pluto's brightness variations even more baffling is how inconsistently they unfold. Earth-based telescopes and spacecraft like New Horizons have documented swings in albedo, the scientific term for reflectivity, that don't always align neatly with Pluto's distance from the Sun. Sometimes the dwarf planet darkens when it should be brightening, or vice versa, hinting at hidden factors beneath the surface. Could underground reservoirs of volatile ices be leaking gases at irregular intervals? Might cryovolcanic vents be sporadically spewing fresh frost onto the terrain, overriding seasonal trends? Or is Pluto's wobbly 120-degree axial tilt stirring the pot, creating climatic chaos that disrupts the expected patterns? The stakes of this mystery go beyond Pluto alone. If volatile ices can reshape a world's brightness so dramatically, it raises questions about other Kuiper belt objects, some of which exhibit similar erratic reflectivity. Are they, too, hiding active sublimation cycles beneath their frozen crusts? And what does this mean for our models of planetary evolution in the solar system's coldest reaches? Pluto's flickering light isn't just a curiosity, it's a beacon, illuminating the dynamic, ever-changing nature of worlds we once dismissed as static ice balls. Every shift in its glow whispers secrets about the delicate interplay of chemistry, climate, and time in the farthest corners of our cosmic neighborhood. Perhaps the most tantalizing clue lies in the way Pluto's brightness changes aren't smooth but patchy, as if the dwarf planet is a puzzle whose pieces are transforming at different rates. High-resolution images reveal intricate mosaics of light and dark, where fresh ice gleams beside ancient stains in a dance that defies prediction. Some scientists compare it to a slow-motion kaleidoscope, where the patterns shift not in seconds but in centuries, driven by forces we're only beginning to decipher. One thing's certain, Pluto's ever-changing face is proof that even in the deepest freeze, change is the only constant. And somewhere in those fluctuations lies the key to understanding not just this enigmatic world, but the hidden lives of countless others lurking in the shadows beyond. One of the most bewildering discoveries on Pluto wasn't found in its icy plains or jagged mountains. It was hiding in plain sight, stretching across the frozen landscape like whispers from an alien weather system. Dunes, not the towering sand dunes of Earth's deserts, but fields of granular methane or nitrogen particles, sculpted into delicate ripples by winds so faint they shouldn't exist. This is the paradox of Pluto's dunes. How can a world with an atmosphere 100,000 times thinner than Earth's possibly muster the force to carve such intricate patterns? The answer lies in a delicate cosmic ballet where gravity, chemistry, and barely their breezes conspire to create the impossible. When New Horizons beamed back images of these dune-like features near Pluto's mountain ranges, scientists initially doubted their eyes. Wind-driven dunes require two things: loose particles and enough atmospheric pressure to lift and transport them. On Mars, where the air is just 1% as thick as Earth's, dunes make sense. But Pluto's atmosphere is so sparse it's practically a vacuum, so how are these formations even possible? The secret might lie in Pluto's exotic ices. Methane and nitrogen, frozen solid in the dwarf planet's deep chill, could be turning directly from ice to gas under the faint sunlight, creating micro-explosions that launch tiny grains into the air. With Pluto's gravity just 6% of Earth's, even the gentlest upward nudge could keep particles aloft long enough for whisper-thin winds to push them into sinuous ridges. But the real marvel is the scale of these dunes. Some span miles, their undulating forms mirroring the dunes of Namibia or Arabia, except here, the sand might be grains of methane ice as fine as powdered sugar. Computer models suggest Pluto's winds, though feeble, could reach speeds of up to 22 miles per hour during peak sublimation periods, when surface ices vaporize and briefly thicken the atmosphere. That's barely a breeze on Earth, but on Pluto, it's enough to send particles skimming across the ground in low, graceful arcs. Over centuries, these sporadic puffs of wind could pile grains into the patterns we see today, like a slow-motion etch-a-sketch operated by the universe itself. Yet puzzles remain. Why do these dunes cluster near mountain ranges like Al Idrisi Montes? One theory suggests the peaks act like wind tunnels, funneling and accelerating the already faint breezes into concentrated currents capable of shaping the surrounding plains. Another idea points to temperature gradients where sunlight warms the dark slopes of mountains faster than the bright icy plains, creating localized winds that dance around the terrain like invisible sculptors. The dunes might also be ephemeral, forming and vanishing over millennia as Pluto's atmosphere expands and collapses with its eccentric orbit. What's undeniable is that these features blur the line between possible and impossible. They challenge our assumptions about where wind-driven geology can occur, proving that even the faintest whispers of an atmosphere can leave lasting fingerprints on a world. And if Pluto, a tiny outpost at the solar system's edge, can host dunes, what other impossible phenomena might be waiting in the darkness, on worlds we've yet to explore? One thing's certain, Pluto's dunes aren't just a scientific curiosity. They're a testament to the universe's endless creativity, rewriting the rules of planetary science one grain at a time. Charon's surface tells a violent story, a frozen testament to forces that once tore this moon apart from the inside. Stretching across its rusty plains are vast chasms and scarps, some deeper than the Grand Canyon and hundreds of miles long. These aren't random cracks, they form a sprawling network of fractures that wrap around Charon like the seams of an overinflated basketball. The most striking of these, Serenity Chasma, could swallow Everest whole with room to spare. But what caused such catastrophic stretching? The leading culprit might be something unexpected lurking beneath the ice, an ancient ocean that froze solid, expanding with such force it shattered Charon's crust in its escape. Picture this scenario billions of years ago. Early in its history, Charon may have harbored a subsurface ocean, kept liquid by heat from radioactive decay or the lingering warmth of its formation. But as the moon cooled, that ocean began to freeze. Unlike most substances, water expands when it solidifies, a quirk of physics that, on a planetary scale, becomes apocalyptic. The growing ice would have exerted immense outward pressure, thrusting Charon's frozen shell upward until it split like an overfilled water balloon. The result? A global system of troughs and ridges, with some areas lifted higher than others as the crust buckled under the strain. Yet this expansion didn't happen uniformly. New Horizons maps reveal that Charon's fractures are concentrated in its equatorial belt, while the poles remain relatively unscathed. This suggests the moon's crust might have been thinner near the middle, like an eggshell with a weak spot, allowing the ice beneath to rupture outward more easily. The fractures also intersect at sharp angles, forming a polygonal mosaic that hints at multiple episodes of cracking, as if Charon endured not one, but several violent reconfigurations over eons. But here's where the mystery deepens. If Charon's ocean fully froze, why does its surface show signs of recent geological activity? Some valleys appear smoothed, as if material oozed to fill them in long after the initial fracturing. Could residual slush or ammonia-rich antifreeze have lingered beneath the ice, keeping parts of the ocean malleable enough to lubricate slow-motion landslides? Or did tidal flexing from Pluto's gravity, back when the two worlds orbited closer together, reopen old wounds, creating secondary surges of expansion? The stakes of this puzzle extend far beyond Charon. If freezing oceans can reshape moons this dramatically, it raises questions about other icy worlds like Europa or Enceladus, where subsurface seas still exist today. Will their futures mirror Charon's past, and could similar fractures hide on distant Kuiper belt objects waiting to be discovered? Every crevasse on this moon is a frozen echo of chaos, a reminder that even in the stillness of space, change is the only constant, and violence can be written in ice. Pluto's surface is a gallery of oddities, but few are as perplexing as the strange X-shaped features scattered across its icy plains. These enigmatic markings, resembling cosmic etchings or celestial graffiti, appear in clusters where nitrogen and methane ice dominate, often near the edges of sprawling glaciers or in regions pockmarked by sublimation pits. Unlike the linear fractures or polygonal patterns seen elsewhere, these X's seem deliberate, as if some unseen force pressed a stamp into the dwarf planet's skin. But the truth behind their formation is far more fascinating than intentional design. One leading theory ties these X's to Pluto's volatile ices vanishing into thin air. As sunlight warms the surface, nitrogen and methane sublimate directly from solid to gas, leaving behind uneven pits and depressions. Over time, adjacent pits might expand and merge, their walls intersecting at sharp angles to form those distinctive cross-like shapes. Imagine two bubbles in a pancake batter growing until they pop into one another, the edges where they meet creating a temporary X before collapsing further. On Pluto, this process unfolds over centuries, with the faintest solar heat sculpting the ice into fleeting, geometric scars. Yet sublimation alone might not explain the full story. Some researchers argue tectonic forces could be at play. Pluto's crust, strained by tidal interactions with Charon or the freezing and expansion of subsurface ices, might be fracturing in ways that create intersecting fault lines. These cracks, filled with darker tholins or fresher ice, would stand out against their surroundings, forming X's as they cross. The New Horizons team spotted similar features on Neptune's moon Triton, where crustal stretching and sublimation collaborate to carve bizarre landscapes. But Pluto's versions are larger and more pronounced, suggesting a unique interplay of geology and climate. Even more intriguing is the possibility that these X's are ephemeral snapshots of a transient process. Unlike craters or mountains, which persist for eons, these markings might vanish within millennia as sublimation erases them or fresh ice buries them. Their presence in relatively young terrains, like the fringes of Sputnik Planitia, hints that they're actively forming today, a live demonstration of Pluto's dynamic surface evolution. What's particularly striking is how these features challenge our understanding of planetary surfaces. Normally, we expect erosion to create randomness, jagged cliffs, chaotic pits. Yet here, Pluto seems to favor geometry, crafting X's with an almost mathematical precision. Could seasonal wind patterns, no stronger than a sigh, be guiding the sublimation process along invisible paths? Or do the properties of methane ice itself, brittle yet responsive to subtle stresses, predispose it to fracture in these angular ways? The X's serve as a reminder that Pluto, for all its stillness, is a world in flux. Every marking is a clue, a whisper of processes unfolding in slow motion, where ice becomes gas, cracks merge, and landscapes rewrite themselves in symbols we're only beginning to decode. And somewhere in their crossed lines lies a deeper truth about how even the coldest, most distant worlds remain anything but frozen in time. Pluto's methane isn't playing by the rules. It clings stubbornly to some regions while ghosting others entirely, leaving behind a patchwork of ice and emptiness that defies easy explanation. Take the western half of Tombaugh Regio, where methane frost blankets the landscape like a fine dusting of snow, versus the darker highlands of Cthulhu Macula, where the same compound is conspicuously scarce. These aren't random variations, they're clues to a hidden drama of atmospheric currents, chemical warfare, and seasonal sleight of hand unfolding across the dwarf planet's surface. The mystery starts with Pluto's extreme seasons. As the dwarf planet wobbles through its 248-year orbit, sunlight strikes different latitudes at varying intensities, turning certain areas into temporary cold traps. Methane, along with nitrogen and carbon monoxide, sublimates from warmer zones and migrates toward colder ones, condensing back into frost like a slow-motion weather cycle. But this doesn't explain why some equally cold regions end up starved of methane while others stockpile it. The answer might lie in Pluto's capricious winds. Though its atmosphere is thinner than a spider's web, trace breezes, some clocking a mere few miles per hour, could be enough to redirect methane particles towards specific areas, depositing them like cosmic snowdrifts against mountain ranges or in topographic lows. Then there's the role of chemical betrayal. Methane on Pluto isn't just frozen, it's under constant assault from solar radiation. When ultraviolet light hits methane molecules, it breaks them apart, leaving behind free hydrogen atoms and carbon fragments that recombine into heavier hydrocarbons like ethylene and acetylene. Over time, these byproducts polymerize into tholins, the dark, reddish gunk staining Pluto's equatorial belts. In regions like Cthulhu Macula, this process might be devouring methane faster than it can be replenished, leaving behind a wasteland of complex organics where methane once thrived. But chemistry alone doesn't account for the stark divide. Some scientists point to Pluto's subsurface geology as the missing piece. Methane could be seeping from reservoirs deep underground, venting through cracks or cryovolcanic fissures in concentrated patches. Areas with active resurfacing, like Sputnik planetars churning nitrogen glaciers, might bury methane too quickly for it to accumulate, while older, stagnant terrains let the ice linger. There's also the wild card of methane clathrates, ice like cages of water molecules trapping methane gas, which could stabilize the compound in some regions while leaving it vulnerable to destruction in others. The most tantalizing possibility: Pluto's methane distribution might be a snapshot of an ongoing battle between creation and destruction. In the bright, youthful plains, fresh methane frost could be constantly renewed by atmospheric transport or underground sources. In the darker, ancient highlands, radiation and chemistry conspire to erase it. It's a reminder that even on a world 3 billion miles from the sun, the balance between ice and emptiness is never static. It's a dance of forces we're only beginning to map, one frozen molecule at a time. Pluto should be frozen solid, a lifeless ball of ice drifting through the perpetual night of the Kuiper belt. Yet thermal measurements tell a different story, revealing a dwarf planet that stubbornly clings to more warmth than anyone predicted. When New Horizons scanned Pluto's surface, it detected subtle heat signatures that didn't match the expected deep freeze temperatures for a world so far from the sun. Some regions, particularly around active areas like Sputnik Planitia, registered just enough warmth to hint at hidden energy sources beneath the ice. This anomaly has sparked a fierce debate. Is Pluto generating its own heat, or is something else at play in this cold but far from dead world? One camp argues for internal heat, pointing to radioactive decay in Pluto's rocky core as the likely furnace. Elements like uranium, thorium, and potassium, common in planetary interiors, release energy as they break down over billions of years. On Earth, this process drives plate tectonics and volcanic activity. On Pluto, it might maintain just enough warmth to keep nitrogen glaciers flowing and subsurface slush from fully solidifying. There's also the wild card of tidal heating. Pluto and Charon are locked in a gravitational dance so tight that their mutual tugging could flex their interiors, generating friction like a cosmic stress ball squeezed over eons. While Charon's stretched and fractured surface bears witness to this strain, Pluto's smoother terrain suggests its heat might be distributed differently, perhaps pooling in reservoirs beneath its icy shell. But skeptics propose a simpler explanation. Pluto's surface properties could be playing tricks on thermal sensors. The dwarf planet's patchwork of bright and dark terrains absorbs and reflects sunlight unevenly. Tholin-stained regions like Cthulhu Macula soak up solar energy like a black t-shirt on a summer day, while the gleaming plains of Sputnik Planitia act like a mirror, bouncing most light back into space. This uneven heating might create localized warm spots without requiring any internal furnace. Even Pluto's hazy atmosphere could be a factor. Those towering layers of tholins might trap infrared radiation like a thin but effective blanket, preventing heat from escaping as quickly as models predict. The stakes of this debate stretch beyond Pluto alone. If internal heat persists in a world this small and distant, it reshapes our understanding of how planetary bodies age. Moons like Europa and Enceladus owe their subsurface oceans to tidal heating, but Pluto lacks the massive gas giant needed to generate such forces. Could other Kuiper belt objects harbor similar warmth, hiding liquid layers beneath their icy surfaces? And what does that mean for the potential of life in these frozen outposts? Until another mission reaches Pluto, its thermal secrets will remain tantalizingly out of reach, a reminder that even in the darkest corners of the solar system, cold is never just cold, and heat can come from the most unexpected places. One of Pluto's most haunting geological features isn't a mountain or a glacier. It's a sprawling network of fractures nicknamed the spider for its eerie, leg-like tendrils radiating outward from a central point. This bizarre formation, located near Pluto's north pole, looks less like a natural landform and more like something cracked open from within, as if the dwarf planet's icy shell couldn't contain the pressures lurking beneath. Each of the spider's fractures stretches dozens of miles long, slicing through the terrain in perfectly straight lines that converge like the spokes of a wheel. But what force could carve such precise, radial scars into a world where ice is supposed to be brittle and unmoving? The answer might lie beneath the surface, literally. One leading theory suggests that subsurface material, possibly a pocket of slushy nitrogen or even a buried ocean, once pushed upward with enough force to fracture the overlying ice. Imagine a balloon inflating slowly under a sheet of frozen mud. As pressure builds, the surface cracks in a star-like pattern. On Pluto, this process would unfold over millennia, with the balloon being a reservoir of semi-liquid material oozing upward through weaknesses in the crust. The fracture's razor-straight lines hint at a single catastrophic rupture event rather than gradual erosion, as if something beneath Pluto's skin suddenly gave way. But there's another, even more intriguing possibility. Tidal forces from Charon could be the unseen sculptor. Pluto and Charon are locked in a gravitational dance so intimate that their mutual tugging creates stresses far beyond what most moons exert on their parent bodies. Over billions of years, these relentless tugs might have flexed Pluto's crust like a sheet of glass rubbed between two hands, generating enough tension to fracture the ice in radial bursts. The spider's location near the pole adds weight to this idea. Tidal stresses concentrate at high latitudes, making these regions more prone to cracking under strain. What makes the spider truly puzzling, though, is its uniqueness. While other icy worlds like Europa or Enceladus sport fractures, none exhibit this exact radial symmetry. Even Pluto's other crack networks, like the sprawling canyons of Serenity Chasma on Charon, follow more linear or chaotic paths. The spider's geometric precision suggests an exceptionally localized stress source, perhaps a cryovolcanic plume that failed to fully erupt, leaving behind only the fractures as a clue. Or maybe it's the ghost of an ancient impact where shockwaves spiderwebbed through the ice without leaving an obvious crater. Then there's the question of timing. Some fractures on Pluto, like those in Sputnik Planitia, appear fresh and uneroded, hinting at recent activity. But the spider's fractures are filled with darker material, likely tholins that have drifted in over eons, implying these cracks could be relics of a much older era. If so, they're a frozen snapshot of a time when Pluto's interior was warmer and more dynamic, capable of generating the pressures needed to split its shell from within. Whether born from subterranean upheaval or celestial tug of war, the spider is a reminder that Pluto's surface is just the crust of a deeper mystery. Every fracture is a whisper from the dwarf planet's hidden depths, a place where ice, heat, and gravity conspire to sculpt landscapes stranger than fiction. And as long as features like this remain unexplained, Pluto will keep its place as one of the solar system's most compelling enigmas. Amid the vast, icy expanse of Sputnik Planitia, Pluto's heart-shaped plain, lies one of the solar system's most surreal landscapes: floating hills. These towering chunks of water ice, some as large as Manhattan, drift like cosmic icebergs across a sea of solid nitrogen, their jagged peaks jutting above the frozen surface as if suspended by invisible strings. But here's the twist: these hills aren't just passively bobbing along. Their movements, captured in stunning detail by New Horizons, hint at a hidden turmoil beneath Pluto's skin. Convection currents churning so slowly they reshape the world over millennia. The secret to these drifting monoliths lies in the bizarre physics of Pluto's ices. While water ice is dense and rigid, forming the bedrock of the dwarf planet, nitrogen ice is softer and more buoyant, behaving like a very thick fluid under Pluto's weak gravity. This creates a paradoxical scenario where heavier water ice literally floats atop lighter nitrogen deposits, like a rock resting on a vat of frozen molasses. But the real magic happens beneath. Heat from Pluto's interior, whether leftover from radioactive decay or tidal interactions with Charon, gently warms the nitrogen ice at the base of Sputnik Planitia. As it softens, it begins to rise in sluggish plumes, pushing older, colder material aside in a process akin to a lava lamp's hypnotic dance. These convection cells, each spanning dozens of miles, are what likely jostle the hills into motion, nudging them across the plain at speeds measured in inches per year. What's truly baffling is how these hills cluster. Some gather in loose chains, tracing the edges of convection cells like crumbs caught in a whirlpool. Others stand solitary, their paths meandering unpredictably as subsurface currents shift. New Horizons even spotted chains of hills aligned like beads on a string, suggesting they once belonged to shattered mountain ranges now eroded into fragments carried apart by the nitrogen's flow. The tallest of these hills, nicknamed Challenger Cols, rises over 2 miles high, a floating Everest casting shadows across the gleaming ice below. Yet the mystery deepens when you consider the hill's composition. Spectroscopy reveals they're not pure water ice but coated in a thin veneer of methane, possibly frost deposited as atmospheric gases condense onto their cold surfaces. This raises a tantalizing question. Could these hills be actively growing, their methane jackets thickening as they drift? Or is the methane merely a fleeting garnish, sublimating away under Pluto's faint sunlight only to be replaced anew? The answer might lie in the hills' distinctive shapes, some sharp and angular, others rounded like melted sugar cubes, hinting at different ages or exposure to sublimation's eroding touch. The implications stretch far beyond Pluto. If convection can move hills on a world with barely 1/15 of Earth's gravity, what other geologic rulebooks might need rewriting? Similar processes could be at work on Neptune's moon Triton or Kuiper belt objects like Eris, where volatile ices might also flow in slow, unseen rivers. Even Earth's own glaciers, though made of water ice, offer a faint echo of this phenomenon, just at temperatures and speeds unimaginable in Pluto's deep freeze. Perhaps the most poetic detail is the hill's impermanence. Unlike the static mountains of Mars or the Moon, Pluto's floating hills are transient features, destined to eventually crumble, merge, or vanish as convection reshapes their icy raft. They're not just geological oddities, they're fleeting waypoints in a cycle as old as the solar system itself, where heat, ice, and time conspire to turn solid ground into something alive with motion. And as they drift, they carry with them a silent testament to the fact that even in the farthest reaches of space, nothing ever truly stands still. Pluto's haze layers are cosmic chameleons shifting between ethereal blues and deep reds depending on who's looking and how. When New Horizons captured Pluto backlit by the sun during its flyby, the haze appeared as a mesmerizing blue halo reminiscent of Earth's skies. Yet Earth-based telescopes and some forward scattering observations often depict the same layers with a reddish tint. This isn't a camera trick or an illusion. It's a masterclass in light physics and atmospheric chemistry playing out 3 billion miles from the sun. The secret lies in the size and composition of the haze particles themselves. When sunlight encounters Pluto's upper atmosphere, it collides with tholins, those complex organic molecules formed when UV radiation breaks apart methane and nitrogen. These particles are far larger than gas molecules but still microscopic, averaging just a few hundred nanometers wide. Here's where the magic happens. Blue light has shorter wavelengths and scatters more easily off tiny particles, a phenomenon called Rayleigh scattering, the same effect that paints Earth's sky blue. When New Horizons observed the haze with the sun behind it, that scattered blue light dominated the view, creating that iconic cerulean glow. But tilt the angle and the story changes. From Earth or during certain spacecraft observations, sunlight reflects off these particles at different angles, emphasizing longer wavelengths like reds and oranges. Larger tholin clusters, which grow over time as molecules stick together, absorb more blue light and reflect reddish hues, like dust in a sunset. The same haze can appear crimson when viewed head-on because the particle's composition favors absorbing shorter wavelengths and bouncing back the rest. There's another twist to altitude matters. Pluto's highest haze layers, where particles are freshly formed and smaller, scatter more blue light. Deeper down, as tholins coagulate into larger, fluffier aggregates, they transition to reddish tones. This vertical gradient means the haze isn't a single color but a stacked rainbow, with blue dominating the top and red seeping through below. Seasonal changes add another layer, literally. When Pluto's atmosphere swells during its closest approach to the Sun, increased methane concentration turbocharges tholin production, potentially shifting the haze's average color toward red as particles grow more abundant and complex. The real kicker, this color dance isn't just cosmetic. It reveals the haze's role in Pluto's climate. Blue scattering particles high up likely cool the atmosphere by reflecting sunlight, while reddish tholins lower down absorb heat, creating subtle temperature gradients that might drive atmospheric circulation. Every shift in hue is a clue, a fingerprint of processes that balance Pluto's tenuous air between freezing collapse and fragile persistence. And somewhere in that interplay of light and chemistry lies the answer to why this tiny world's sky refuses to choose just one shade. Pluto's surface isn't just cracked or cratered, it's slipping. Across the dwarf planet's tortured terrain, entire blocks of crust appear to have broken free and slid for miles, leaving behind jagged scars and displaced plateaus that look like pieces of a frozen jigsaw puzzle shoved out of place. These sliding terrains rank among Pluto's most perplexing geological features, hinting at a subsurface world where solid ground behaves more like a sled on wet ice than the rigid bedrock we'd expect from a distant, icy world. The most dramatic example sprawls across Virgil Fosse, a fracture zone northwest of Sputnik Planitia. Here, massive slabs of water ice, some larger than cities, have sheared off along fault lines and skidded sideways, their edges crumpled like the hood of a wrecked car. What makes this movement so baffling isn't the fracturing itself, icy crusts crack under stress, but the apparent ease with which these multi-mile thick slabs slid across the landscape. On Earth, such movement requires lubrication, water, magma, or loose sediment reducing friction between tectonic plates. But Pluto's surface averages -390 degrees Fahrenheit, far too cold for liquid water to persist. So what greased the skids? The leading suspect is nitrogen ice. While water ice forms Pluto's rigid foundation, pockets of nitrogen ice lurking beneath the surface could have temporarily softened under pressure or heat, acting as a geological Teflon. When stress built up in Pluto's crust, perhaps from tidal forces with Charon or the freezing expansion of buried ices, these nitrogen deposits might have transitioned into a semi-fluid state, allowing overlying water ice slabs to glide with startling ease. Imagine an ice cube sliding across a countertop after you blow on it to melt the underside momentarily, except on Pluto, the breath comes from internal heat pulses or seasonal temperature shifts, and the countertop stretches for hundreds of miles. But nitrogen alone might not tell the full story. Some researchers propose that ammonia detected elsewhere in the Kuiper belt could be mixing with Pluto's subsurface ices. Ammonia acts as a potent antifreeze, lowering the melting point of water ice by up to 100 degrees. Even trace amounts could create briny, slushy layers capable of lubricating fault zones for geological timescales. There's also the wild card of clathrate hydrates ice cages trapping gases like methane, which remain stable at Pluto's temperatures but become slippery when disturbed. The implications ripple beyond mere geology. If Pluto's crust can slide en masse, other mid-sized icy bodies might share this behavior. Neptune's moon Triton, often considered Pluto's sibling, shows similar fracture patterns. Even Mars' northern plains bear scars of possible, lubricated crustal movement from ancient ice ages. Each displaced slab on Pluto becomes a clue, not just to the dwarf planet's hidden dynamics, but to a universal mechanism shaping icy worlds across the cosmos. What remains haunting is the scale. Some shifted blocks stretch over 30 miles long, their migration preserved in eerie detail like freeze frames of an avalanche. The energy required to move such masses suggests Pluto's interior was, or perhaps still is, far more dynamic than we imagined. Whether driven by cryovolcanic surges, tidal flexing, or the slow-motion collapse of underground cavities, these sliding terrains prove one thing. Even in the solar system's deepest freeze, solid ground is never truly solid, and entire landscapes can go skidding into the unknown. Pluto's moons don't just orbit, they tumble through space with the grace of a tipsy tightrope walker, spinning and wobbling in ways that defy every rule of celestial mechanics. While most moons in the solar system, including our own, are tidally locked, showing one face permanently to their parent planet, Pluto's smaller satellites like Nix and Hydra flip and rotate so chaotically that their north and south poles swap places without warning. This isn't just a minor quirk, it's a full-blown rebellion against the gravitational order, and it hints at a violent, unstable past that reshapes how we think about moon formation in the outer solar system. The root of this chaos lies in Pluto's lopsided partnership with Charon. Unlike Earth and its moon, where our satellite is tiny compared to the planet, Charon is so massive relative to Pluto that the two essentially orbit a shared point in space, a barycenter located outside Pluto's surface. This creates a gravitational tug-of-war so intense that the smaller moons caught in the crossfire are jostled like rubber balls in a hurricane. Normally, tidal forces would stabilize a moon's rotation over time, but Pluto's erratic gravitational field, shaped by Charon's competing pull, keeps Nix, Hydra, Kerberos, and Styx in a perpetual state of disarray. But the real shocker is how this turbulence might trace back to the moon's origins. One leading theory suggests these tiny worlds weren't born alongside Pluto and Charon, but are instead the shattered remnants of a cataclysmic collision. Billions of years ago, a massive impact could have launched debris into orbit, where it coalesced into the irregular, rubble-pile moons we see today. Their lumpy shapes, more like potatoes than spheres, support this idea, as does their bizarre rotation. Without the stabilizing mass of a solid core, these agglomerations of ice and rock are at the mercy of even the faintest gravitational nudges, tumbling like leaves in the wind. Yet not all the moons are equally chaotic. Kerberos and Styx, the smallest of the bunch, exhibit peculiar synchronicity, their orbits locked in a delicate resonance that suggests their paths were sculpted by ancient interactions, perhaps collisions or close encounters that ejected other moons entirely. Meanwhile, Nix and Hydra spin so unpredictably that their day lengths might vary wildly over centuries, their axes tilting like unbalanced tops. The implications stretch far beyond Pluto. If such small, icy moons can resist tidal locking, it raises questions about other binary systems in the Kuiper belt, or even exoplanetary moons orbiting distant stars. Their chaos might be the key to unlocking secrets of the solar system's violent youth, when collisions were commonplace and orbits were far less orderly than they appear today. What's most striking is how these tiny moons, once dismissed as static afterthoughts, are proving to be dynamic worlds in their own right, where gravity, chance, and time conspire to create a ballet unlike anything else we've witnessed. Every erratic spin and wobble is a clue, a whisper from the solar system's past, reminding us that even in the coldest, darkest reaches, there's no such thing as stillness. Pluto and Charon might orbit the same point in space, but their surfaces tell wildly different stories, one of icy dynamism, the other of frozen decay. While Pluto dazzles with nitrogen glaciers, hazy skies, and possible cryovolcanoes, Charon's landscape is a study in stillness, its ancient craters and cracked plains barely touched by geological renewal for billions of years. This cosmic odd couple forces us to confront a fundamental question: how can two worlds forged from the same collision and bound by gravity diverge so dramatically? The answer lies in a cocktail of size, chemistry, and celestial betrayal that reshaped their fates. Start with Pluto's undeniable advantage: mass. Though small by planetary standards, Pluto is still twice as hefty as Charon, granting it a critical reserve of internal heat. Radioactive elements like uranium and potassium in its rocky core continue to decay, generating warmth that keeps volatile ices like nitrogen and methane mobile on the surface. Charon, meanwhile, lacks the mass to retain such heat. Its core likely cooled rapidly after formation, freezing any subsurface ocean solid and shutting down the geologic engine that might have refreshed its face. That freezing process itself left scars. Charon's canyons, like Serenity Chasma, are thought to be the product of a global icequake as its ocean expanded while solidifying, cracking the moon's crust like an overfilled water bottle left in a freezer. But mass isn't the only divider. Composition plays a starring role. Pluto's surface is a palette of volatile ices: nitrogen, methane, and carbon monoxide that sublimate, flow, and recondense in response to faint sunlight. These ices act like geological lubricants, enabling the slow-motion ballet of glaciers and convection cells in Sputnik Planitia. Charon, by contrast, is cloaked in water ice and ammonia hydrates, materials far more stable in the cryogenic vacuum of the Kuiper belt. Without volatile ices to fuel activity, Charon's surface became a museum of its earliest days, its craters preserved in icy amber. Then there's the wrench thrown into their relationship: tidal forces. Early in their history, Pluto and Charon's gravitational tug-of-war likely generated enough friction to heat both worlds. But as their orbits circularized and synchronized, the energy faded first for Charon, locking it into geologic stasis, while Pluto's greater mass and volatile chemistry bought it extra time. The irony is brutal. The same bond that brought them together ultimately starved Charon of the forces that might have kept it alive. Yet Charon isn't entirely lifeless. Its polar stain, Mordor macula, hints at stolen atmosphere, methane that escaped Pluto only to freeze onto Charon's poles, where radiation cooked it into dark tholins. Even in stillness, Charon bears the fingerprints of its partner's vitality. This dichotomy, Pluto as a churning, evolving world, Charon as a frozen archive, offers a masterclass in how chance and physics shape destiny. For every planet or moon, the line between dynamism and stagnation is razor-thin, written in the language of heat, ice, and time. Pluto has spent the last decade rewriting the rulebook on what we thought we knew about distant worlds. From its heart-shaped plains of shifting nitrogen ice to its vanishing atmosphere, from towering blades of methane taller than skyscrapers to the possibility of hidden oceans lurking beneath its crust, every mystery we've uncovered only deepens the enigma. Think about it, a world where glaciers flow without liquid water, where dunes form in an atmosphere thinner than a dream, where X-shaped scars etch themselves into the landscape like cosmic hieroglyphs waiting to be decoded. This isn't just a quirky dwarf planet, it's a laboratory for the most extreme physics our solar system has to offer. Consider how Pluto defies expectations at every turn. Its moons tumble chaotically instead of obeying gravitational norms. Its surface slides in colossal blocks, as if the very ground is skating on unseen layers of slush. Even its color palette, those eerie red tholin stains against blinding white ice, tells a story of chemical warfare playing out over eons. And let's not forget the spider, that bizarre fracture system radiating from a single point like cracks in a shattered windshield, hinting at pressures we still don't fully understand. These aren't just oddities, they're seismic revelations proving that even in the farthest reaches of the Kuiper belt, worlds can be as dynamic as Earth. What's truly groundbreaking is how Pluto's mysteries force us to rethink planetary science entirely. Traditional models assumed small, cold worlds like this would be geologically dead, frozen time capsules preserving the early solar system. Instead, we found a place where nitrogen glaciers rewrite landscapes, where cryovolcanoes might still ooze icy slurries, and where an atmosphere collapses and rebuilds like a cosmic accordion. Pluto doesn't just challenge the definition of a planet, it shatters our assumptions about where geologic activity, and maybe even the ingredients for life, can exist. If these processes thrive on a tiny world 3 billion miles from the Sun, what other surprises are hiding in the darkness? That's the magic of exploration. Every answer New Horizons provided sparked a dozen new questions, and that's exactly how science should work. Maybe your team's subsurface ocean, convinced there's liquid water beneath Sputnik Planitia. Or perhaps the floating hills drifting across nitrogen glaciers captured your imagination. Whatever mystery fascinates you most, that curiosity is what drives discovery forward. So keep wondering, keep questioning, because Pluto's greatest lesson might just be that the universe is far stranger, far more inventive than we ever dared to imagine. If you've enjoyed this deep dive into Pluto's enigmas, don't miss out on more cosmic revelations. Hit subscribe to join us as we unravel other space mysteries, from the volcanoes of Io to the icy geysers of Enceladus. And drop a comment below, tell us which Pluto mystery blew your mind the most. Was it the creeping glaciers, the chaotic moons, that haunting blue haze? The conversation doesn't end here. After all, Pluto's story is still being written, and the next chapter could change everything we think we know about the solar system's wild frontier.